So this is Practical Malware Analysis, and today we're going to talk about assembly code. And we're going to talk about x86 assembly code, and I've added a project that I just wrote today about ARM assembly code for those people like me who have ARM processors. So let's start with the lecture stuff. All right, so we've been here before. Basic static analysis, you look at the malware without running it and do something like look at the strings or the hash. Then dynamic analysis, you run it and see what it does to a machine. Disassembly is the next step up, where you take the executable instructions, which are in machine language, and somebody is calling me from 800 number. Let me check and see if I'm on mute or something. No, okay, good. All right, it's not just girls. Boys are also affected. Well, I wonder, because the studies have not shown that. Studies have shown it's particularly girls, but...
You need to look at more studies.
Okay, that's good. This good to hear. Yeah, anyway. So disassembly turns the assembly language, machine language instructions into assembly language, which is intended to be human readable, and it's sort of human readable. And then you read through that to find out how the malware works. So here's the levels of abstraction. The author will write in a high-level language like C, so they'll write stuff like this. Then it will get compiled down to binary machine code, which is just hexadecimal codes, and this is all the processor ever uses. And typically the symbols are stripped out, so you don't have the names of variables or names of routines or anything to guide you. And when you disassemble, you turn into this assembly code, which is hard to read, although easier to read than that. Certainly not as easy as that. And this is what you spend most of your time understanding in disassembled code. Now, there are decompilers, which used to be prohibitively expensive, but now Ghidra has a free decompiler, which will actually turn it back into C. But you won't have the names of the methods or the variables. They will just be like var 107, var 108. So it's more readable than assembly code, but still somewhat hard to read. All right, so here's the levels of abstraction you have here. The hardware itself is just XOR, AND, OR, and NOT gates, flipping bits one by one, and all right, and running through program that's hard-coded in binary, or code that is in binary form. Microcode is firmware, which is available to run hardware. Typically, you have microcode on your NIC and microcode on other things. Typically, we don't bother with this with malware, although we are getting firmware malware and boot sector malware. It's a new scary thing, and there's not much of a defense against it, but we're not covering that. We're not having hands-on projects for that in this class yet, although it's coming. Now, machine code, assembly code really, has opcodes, which tell the processor to do things, and this is what is created when you compile a high-level language like C. Then low-level languages are assembly languages like humans have, where you have individual instructions here which will turn into one machine language instruction. And so that's what disassemblers create. This is the highest level language that can be reliably recovered from malware, although, as I say now, a decompiler will actually create something more like source code, which used to not be common. Now it's becoming more common. And then, of course, what programmers actually use is C and C++ and Java and Python and Rust and all those things, which are intended to be very easy for a human to read and understand. All right, and then there are interpreted languages, which are never compiled at all. Typically Python and Java, which are not compiled into machine code. They're translated into bytecode, which, like Java, is translated into bytecode, which is run in a Java virtual machine, which is why Java code can run on multiple operating systems. You can run the same program on Windows or Linux because you run it in a Java virtual machine. The penalty is it runs much slower. But that's the game. It's actually interpreted at runtime. All right, so for reverse engineering, you take binary executables and you disassemble them into assembly language. And IDA-Pro is the most popular disassembler, although there are competitors, x86, debug, and we'll see some others. All right, there's different assembly language for each type of processor. The most common is 32-bit Intel. This may be changing now, but it may not. I mean, at least as of maybe 5 years ago, most malware was 32-bit because there's a lot of 32-bit machines. And if you write 32-bit code, it'll run on 32-bit Windows or 64-bit Windows. Windows always supports one generation back processors for compatibility. Linux, by the way, does not. you can add extra modules to add that feature to Linux, but until you do, it does not support the previous generation of processors. And so most malware is written in 32-bit Intel code to run on either 32 or 64-bit Windows machines. Now, we may be reaching the point where 64 is the most common malware now because very few people are still running 32-bit machines, but there is IoT, all the Internet of Things devices, cell phones and thermostats and smart light bulbs and everything. Most of those are running 32-bit, but typically 32-bit Linux, although there is, I think, a 32-bit Windows intended for that, and some of them may be running 32-bit Windows like payment terminals at your bank and stuff. There are lots of other hardware processors, and the most important one is ARM, which is what I'm using now, and I'll talk more about that later. So anyway, all right, let me just check for comments here. For the P41 project for M1 users. Well, I'll talk about that after the lecture. I'll try and figure that out. All right. Anyway, all right. So x86, you have a CPU, and then you have an arithmetic logic unit and a control unit. So, and you have the main memory, RAM, and I/O devices, and this is also true of ARM and x64. In general terms, this is how it all works. So the control unit fetches instructions from RAM. It uses an instruction pointer. The instruction pointer tells it, here's one of the many disturbing things about this. The main memory includes all the instructions that are going to be processed and all the data that's going to be processed, and there is no distinction made between those two things, which in retrospect was probably a mistake. But as I mentioned before, the fundamental way all these exploits work is you trick the computer into executing something that was not supposed to be code as code, something that came in and was supposed to be text or something. And it doesn't know what anything is. So anyway, the control unit takes the program counter, fetches that instruction from main memory and passes it on to the arithmetic logic unit, which executes it, and then it goes to the next location and the next, and that's how it works. All right, registers are data storage within the CPU, much faster than RAM, but there's only a few of them. The ALU does arithmetic or logic, as you'd imagine, actually does the processing of instructions. And the main memory is here. Now, each program is allocated a region of memory to use. And it's a separate region of memory for each program, so each program should not be able to intrude on the operation of another program. And in there, it's got various segments of memory, places where data sits, places where the code sits, a stack and a heap for a temporary storage of data. All right, so data is value placed in RAM when a program loads. Some 800 phone number keeps on calling me. I doubt an 800 phone number is a student. I think I'll just let it go by. Anyway, all right. These are static variables that are loaded in there. They might be called global. Those are things in the data segment. The code segment is binary machine language that the processor can execute. And the heap is a place where you can store data temporarily and you can deallocate it and reuse the same memory again later as part of your program. And this is where you would put something that is big and only used temporarily. For example, if your program uses the network traffic, you might take the network traffic and put it up there, process it, and then you're done with it, then deallocate it and have the next chunk of network traffic used in the same spot. All right, and the stack is designed for this process where you have a routine that calls a subroutine that calls another subroutine that calls another subroutine. So you're maybe on line 5 of the main program, then you jump to some subroutine, get to line 6 of that program, then you jump to some subroutine, and you're line 2 of that one. So right now, you're partway through processing main, partway through processing the subroutine, and partway through processing the one behind it. So you have to remember where you left off in a dream within a dream, and that's what the stack is for. The stack is designed to let you start a new subroutine, remembering where you left off in the previous one, and make it as deep as you want. And real programs are typically 10 or 20 or 30 layers deep when they run. All right. And you call it a stack frame. You allocate a stack frame for one routine, and then if it calls a subroutine, you put another stack frame on top of it. If that calls one, you put another stack frame on top of it, and when you return, you go back and back and back to emerge from the dream. And this is how everything works. You start with the operating system, you call your main routine, and that's a stack frame on top of the operating system, and every subroutine you call from in there is another stack frame on top of it. All right. So instructions have mnemonics followed by operands. So if I move the ECX register 042, this, now I'm going to move the immediate constant 42 in hexadecimal into this register ECX. This is, I think, the Intel format where you have the source here and the destination there, which is kind of unintuitive, but that's the way it is. So move ECX is B9 in hexadecimal. That's the hexadecimal code for that. So this is B9 42000 because an immediate value of 42 is a 32-bit value. So it has 3 bytes of 0. And it's little endian, just to give you a headache. Instead of putting the most significant number on the left and the least significant on the right, you put the bytes out of order. This is the number of 1s, this is the number of 256s, this is the number of 256 squared, and this is the number of 256 cubed. That's how it works. So it's actually extremely illogical. Not only does it not have the biggest number on the left, it's not monotonic. The least significant bit is the 8th bit. Then these are all 256 times more significant. So from a mathematical point of view, little endian is really strange, but that's what modern processors use. So move ECX 042, the move mnemonic is here that tells you what it does, the destination and the source operands. That's the Intel format. AT&T reverses these two, but Windows code is typically written in the Intel format, looking like this. So let's try a Kahoot, which I should have open here. Aha, and I might. Good. All right. All right. People still coming in. All right, so what part of that instruction is the mnemonic? The move is the mnemonic. All right, the first thing. Move is the most common machine language instruction, and by the way, move is the only thing you need. We've proven that move is NP complete. You can write a code with nothing but move instructions, and boy, if you do, it's really hard to understand. It's a form of obfuscation. People did this to stunt. I'm not aware of any malware actually doing that, but if they did, it would really, really thwart your attempt to disassemble it and understand it. Anyway. All right, so what language does the processor use? It's the only thing it understands. It doesn't know what any of the rest of these are. All right, so what utility would convert a high-level program into an executable file? That's what compilers do. Interpreters translate each command one by one. They don't create an executable file. But that's what compilers do. They create an executable program as a separate file. All right, what's the most common type of assembly language found in malware? And as time passes, this answer will change. The book says it's x86. I begin to question it. Maybe it's x64 now, and someday it may be ARM. But right now, x86 appears to be the most common. All right. All right, so where are local variables stored? These are variables used by one routine, only inside that one routine. Is where they're stored. They only exist while that routine is running, and when it returns, the memory is reused, and those local variables are gone. Let's see. So, good, let's go back to here. All right, so I mentioned this before, big endian would be the most significant byte first. This would be the logical way you write mathematics, so 042 is 60 as a 32-bit value, pardon me. That's a 32-bit value, would be 1, 2, 3 bytes of 0 followed by 42. Now this is logical. The bits on the left are the most meaningful, and the bits on the right are the least significant. But little endian, which is what Intel uses, is this. You take those bytes and put them out of order, which is pretty strange, but that's the way it is. All right. Network data like IP addresses, however, uses big endian. So if you had an address like 192.168.1.101, you'd have to put them in order. So changing the endian from one to another is a fairly common thing you have to do. Yeah, here's the IP address. So 127.0.0.1 would be 7F001. And stored in RAM is this, just to give you all a headache. But sent over the network as that. All right, so immediate operands are fixed values like 0x42. That just means the literal number 42, although it's in base 16. So it's 4 times 16 plus 2, 66, not the decimal value 42. Then there's registers, EAX, EBX, and ECX, because originally, when I started, I used a 6502 8-bit processor, and there was only one register, and it was called A for accumulator because it came from mechanical cash registers and adding machines before there were electric computers, where you would key in prices and press a big button, and it would accumulate the total price. Those mechanical adding machines are what led to the first processors. The microprocessors pretty much did nothing more than what that mechanical adding machine did, and so the only register that existed was the accumulator. As we moved to more and more advanced processors, they added more registers like B, C, and D, and they also got longer, so they went to extended and then extended on the other side too. So this would be the 8-bit register. EAX is extended twice to get it to 32 bits. That's how you ended up with this funny name. And then you can refer to memory addresses. If you put brackets around a quantity, then it is not that literal number, it is the memory address pointed to by that number. So this would take the number in EAX, treat it as an address, and look up that byte of RAM. So the registers are here, EAX, B, C, and D. These are the general purpose registers you can use for anything purpose you want. Then the base pointer and the stack pointer point to the bottom and top of the current stack frame. And the ESI is another general purpose register you can use to count, typically to count your way through an array. And the EIP is the real important one that points to which instruction is going to be processed next. And there's an E-flags register where it stores a bunch of bits that contain binary information like whether the last command resulted in a 0 or not. And you don't usually refer to this directly, but you refer to it indirectly by having a branch instruction, like jump on equal or jump on not equal. Let me check for comments in the Twitch. Intel has announced a plan to remove x86. Wow, that's interesting. News for 16 and 32-bit support. Well, it's interesting to know. Okay, so maybe 32-bit code is on the way out. We'll see. At some date, it'll have to end. All right, so those are the general registers. The segment registers keep track of sections of memory that are hardly ever used. Status flag, I mentioned, used to make decisions. And the instruction pointer is the address of the next instruction to execute. All the general registers are 32 bits in size. So you could refer to EDX, which would be the 32-bit register, or you can refer to 16 bits of it as DX. These 4 registers can also be referenced as 8-bit values, AL and AH. So you can do 8-bit calculations. This would seem kind of pointless. Why would you ever want to do that? The only use I know is when you're writing malware. We use it a lot in exploit development class. This is how you avoid having nulls. Nulls are usually a problem for your exploits, so you often use 8-bit instructions to avoid that. Anyway, so here's EAX with all 32 bits. Here's AX with 16 bits, and here's A low and A high to refer to just 8 bits at a time, all of which are allowed, although you normally only do 32-bit instructions because it's the most efficient way to handle a large amount of data, and that's usually what you want to do in productive programming. But in malware, you use these nasty things to make your code smaller and to avoid bits that make trouble because nulls terminate strings in C. So if your exploit is feeding program code in where a string should go, you want to write program code that doesn't include any nulls, or it will terminate your exploit early. All right. There are some cases in which the general registers are not interchangeable, and that's multiplication and division, which did not exist. When I used 8-bit code, you had to write your own multiplier and divider, but there are multiplication and division, and therefore they use EAX and EDX together to indicate the low and high order words of the results. There are some compilers have conventions that are not absolutely necessary, but typically EAX contains the return value for function calls. So if you call something like string compare or print or read, the return value will be an EAX. So when you come back, you look at EAX to see if it succeeded or failed. So I talked about the flags already. And here's what they are: 0, carry, sign, and trap. These are just record various things, whether the last result resulted in 0, whether it had an extra bit that had to be carried over, if the result was negative, or if you've turned on hardware debugging, you can have a trap flag, which will cause it to do single step through a code. And the extended instruction pointer has the memory address of the next instruction to be executed, and so when you do exploits, buffer overflow exploits, you try to gain control of the EIP. If an attacker can gain control of the EIP, they can control the box. Now they force the particular box into executing code of the attacker's choice, not the code the developer intended. So here's a few simple instructions. The most common one: move source to destination. It'll move from one location to another. So indirect addressing with brackets, EBX means the memory location pointed to by EBX. So here you got move EBX to EAX. That'll just copy whatever's in the EBX register and put it in the EAX register also. Here I'll put literal value 42 in EAX. This will look up that address, 4037C4 in RAM, find whatever is there, and move that into EAX. This will take EBX, interpret it as a memory address, take whatever's in there and put it in EAX, and this will take EBX plus ESI times 4 and move that into there. You see this construction all the time because, to give us all a headache, memory is used 32 bits at a time. That is the word size, but it's addressed 1 byte at a time. So if you want to move a long string of stuff like a graphic image, then you move 4 bytes at a time. So you always have this construction, the start of the string plus the index times 4, moving forward 4 bytes. And it's all because of history. Like I say, originally you had an 8-bit processor, an 8-bit memory, and everything was logical. Then you moved the processor to 16 and 32 and now 64 bits, but the RAM is still counted byte by byte. So that's why you have this very common arrangement of a base address followed by an index counter times 4 to step through word by word as you copy data from one location to another. Let me check for comments online. Nothing new, all right. All right, then there's this weird thing called load effective address, which will calculate EBX plus 8, and instead of moving the contents of that memory location to EAX, it will put the address into EAX. This seems like a strange, pointless thing to do, and this introduces you to the cruelty of this. There are only so many machine language instructions, and often the one you want does not exist, and you have to use something else or combine 2 or 3 to get what you want. So it would seem like there's probably a simpler way to do this, but this is the way they do it in the Intel. Anyway, all right, so here we're going to do move EAX bracket EBX plus 8. So it's going to take EBX, which contains this value, then add 8 to it and go down here. Then it's going to take that value and put it in EAX. That's how it works. All right? So you got everything you need: subtract, add, increment, decrement, multiply, and divide, everything, of course, that you need. NOP is the instruction that might seem pointless, just like the 0 seems pointless when you're learning arithmetic. This is the instruction that does nothing. Now, the original purpose of the NOP instruction was the instructions have different lengths. Remember, the instruction we did back here, this is something particularly strange about Intel processors. This instruction back here, there, move ECX is B9, followed by a 32-bit value, so this is 5 bytes long, which is kind of screwy. Each instruction takes a different amount of bytes. Some instructions must start on a 4-byte boundary. So if you were to have this 5-byte instruction, and then the next one has to start on a 4-byte boundary, you have to skip 3 bytes. That's what NOPs are for. You'd put NOP, NOP, NOP in there to do nothing but fill up those bytes. The NOP instruction does nothing and goes to the next command. That's what it's for. However, it turns out to be extremely useful to attackers because when you are attacking a box with the classic buffer overflow and all other attacks are derived from the buffer overflow, you're feeding in something like a username or a password that's supposed to be text, and you're somehow tricking the processor into executing it as code. Now, when you inject it, somewhere in there you have some of those bytes control the instruction pointer, so you can tell it to go run your code, but you have to know where your code is. Now, what you do is you build a home machine, like a virtual machine, that is close to the server you're attacking, and you try to figure out where the code is. But it's often an approximate process. So typically, you don't know exactly where your code is. So instead of trying to jump to the start of your code, you put in like 1,000 NOPs followed by your code, which is the egg. And then if you can hit anywhere in the NOP slit, it will go NOP, 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 and hit the egg. So that's why one clue that someone is attacking you is they're injecting code that contains a whole bunch of NOPs. So that's one thing people do. One thing, by the way, there's a whole lot of instructions that you could use instead of a NOP. You could just increment EAX and decrement EAX and do that over and over, and it would amount to accomplishing nothing. For some reason, people don't do that very much. They actually use NOPs, and so you can catch their attack by NOP sleds. Anyway, so the stack is where you have data used by one subroutine. And so it's last in, first out. So I say the top of the stack is the stack pointer. The bottom of the stack frame is the base pointer. Push puts data on the stack, making the stack bigger. Pop takes the top data off the stack and makes the stack smaller. So you can enter a function with call or enter. When you do that, it will create a new stack frame when it enters the function with a prologue of the function, which sets aside enough memory to store all the temporary variables needed by that function. When you exit with leave or return, it releases all that memory and returns to resume the program method above it, going to the return value. So consider a small program that does one thing and returns like printf, print something on the screen and then returns. When you enter it, there are prologue instructions at the start that set aside enough room on the stack to store the local variables this program needs. And then there's an epilogue at the end that restores the stack to its original value and finds a return pointer there, which it uses to resume where it left off in the calling instruction. So you have stack frames. Here, for example, Windows is up here in the caller stack frame. Then you run a program by double-clicking on it, like Microsoft Word. So now you have a subroutine from Windows. Then you do something like click print in Microsoft Word, so it calls a print routine. So now you're running Windows, and you're running Word, and you're running a print routine. And when you're done printing, it has to remember where it left off here. And when you're done with Word, it has to remember where it left off here. So that's why you need a separate series of frames, and in this frame is a return pointer telling it where to resume. If I'm able to overflow a variable and change that return pointer, I can take over the box by controlling the instruction pointer, and that's how buffer overflows work. So a stack frame will have stuff like this. It will have your local variables in it, and in here there will also be the return address. So if one of these variables is a string, and I'm able to write beyond the allocated memory for this string, I can overwrite it and change the return address, and that's how you take over the box with a classic buffer overflow exploit, which we'll do a lot of in the 127 class, which will be coming in a couple semesters. You can test or compare two things to see if they're the same. They just set the zero flag if they're equal. And you can branch, like I say, here's jump on zero, jump on not zero. So jump if the last operation resulted in zero, jump if the last operation was not zero. And this is how a couple of machine language instructions will make an if statement. So every C program has a main function, which looks like this. It's main, and it has a certain number of arguments and a pointer to the arrays of arguments. And so here's one, just a C function, copy foo bar. The number of arguments is 3. The first one is the name of the program, the next one is foo, and the next one is bar. That's the structure of a C program, and all the command line commands in Linux are C programs. Let me check for comments online. Nothing new. All right, let's try another Kahoot, which is 4B. All right. Steam heat. Spelled correctly, no less. Worcester. I imagine it must be from the French to abuse written language so badly. All right, so what does that instruction do? does, it takes EBX, interprets it as an address, looks up the contents of that RAM location, and puts it in EAX. This is called indirect addressing. All right. All right, what command retrieves data from RAM? Takes this memory location and puts it in EBX. All right. This one loads the effective address. It doesn't actually pull memory data from memory. All right. What command changes the size of the stack? Push adds data to the stack, making it bigger. All right, which instruction is repeated many times in a buffer overflow attack? Good. All right, which command retrieves data from the stack? All right, and we'll see these. I think I'll do the Jasmine project next to make this more clear because people seem a little confused by it. Michael Chona. CF12